Hello, Jiden. Happy New Year! Hoping you've had a great break and you've enjoyed Christmas and New Year with your family. Welcome 2021 and welcome to New Learnings. So, are you ready? For this week's lesson, our focus will be the segments formed by tangents and secants. So, in this lesson, we will illustrate segments formed by tangents and secants and prove theorems on secant segments and tangent segments. Before diving in on the concepts and the theorems, let us have this scenario. Imagine you are working with a construction crew. A road already exists through a forest that goes over a circular lake. You want to build a new road through the forest that connects this road but does not go through the lake. You are able to measure the road that already exists, and you find that the bridge portion of the road is 5 kilometers. And the portion of the road from the bridge to where the new road will be is 4 kilometers. However, you can't measure the road to be constructed because it is through the forest. You need to find out how long it is to know the quantity of the supplies you will need to build it. How do the relationships among tangent and secant segments facilitate finding solutions to real-life problems and making wise decisions just like the problem given? For us to answer this problem, let us dig deeper with the theorems regarding tangent and secant segments. But before that, let us have a recall regarding those segments. In the previous lesson, a tangent and a secant line have the tangent and the secant segment as its subset respectively. These three figures illustrate the tangent and secant segments. On the first figure, circle E has the segment DW and segment GW as the tangent segments. On the second figure, segment AR and segment NR are secant segments of circle O, wherein segment IR and segment ER are external secant segments. On the last figure, segment CO is a tangent segment while segment YO is a secant segment. Segment NO there is an external secant segment. The idea of those segments is essential in this module since we are to focus on the relationship between the segments formed upon the intersection of the tangent and the secant line. The first theorem regarding these segments is the tangent segments theorem. It states that if two segments from the same exterior point are tangent to a circle, then the two tangent segments are congruent. Given in the figure is circle E, wherein segment BW and GW are the tangent segments which intersect at point W, which is at the exterior of the circle. By this theorem, segment BW is congruent to segment GW, which means the length of those segments are equal. This theorem is true to all pairs of tangent segments which are drawn from the same exterior point in a given circle. The second theorem is called the secant segments power theorem. It states that if two secant segments intersect from an exterior point of the circle, then the product of the lengths of one secant segment and its external secant segment is equal to the product of the lengths of the other secant segment and its external secant segment. On the figure, segment KR and segment NR are secant segments of circle O which intersects at the exterior of the circle. Segment IR and segment ER are their external secant segments respectively. By the secant segments power theorem, the product of the lengths of segment AR and segment IR is equal to the product of the lengths of segment NR and segment ER. Example, in the figure on the right, segment SY and segment EY are secant segments. If SY is equal to 15 centimeters, TY is equal to 6 centimeters, and LY is equal to 8 centimeters, what is the length of segment EY? Since the length of segment EY is unknown on the problem and it illustrates two secant segments, the working equation will be the product of the length of segment SY and segment TY is equal to the product of the length of segment EY and segment LY. To solve for the length of segment EY, we will substitute all the given values on our working equation. Next, simplifying, we have 90 is equal to 8 times EY. And further solving for the length of segment EY, we will divide 90 by 8, which will give us EY is equal to 11.25 centimeters. Therefore, the length of segment EY is 11.25 centimeters. Since the value of x, or the length of segment GA, is unknown, the working equation will be GM times GA is equal to GC times GI. Notice that the length of the whole segments GM and GC are not given on the problem. Instead, the lengths of each secant segments composing those two are given, which are GA, AM, GI, and IC. So the working equation will become the quantity of GA plus AM multiplied by GA is equal to the quantity of GI plus IC multiplied by GI. Substituting the lengths given on the problem, we have the quantity of x plus 6 times x is equal to the quantity of 8 plus 6 times 6. Simplifying both sides of the equation, we will have x squared plus 6x is equal to 14 times 6, which will be further simplified to x squared plus 6x is equal to 84. Isolating all the values on the left to form a quadratic equation, it will become x squared plus 6x minus 84 equals 0. Since the value of x is unknown and we have formed a quadratic equation, we will solve for its factors. We will be using the quadratic formula since it is not a perfect square trinomial. Solving for the value of x, use a is equal to 1, b equals 6, and c is equal to negative 84. Substituting these values to the quadratic formula, we have x is equal to negative 6 plus minus the square root of 6 squared minus the product of 4, 1, and negative 84 all over the product of 2 and 1. Simplifying, we will have x is equal to negative 6 plus minus the square root of 36 minus negative 336 all over 2. Adding the quantities under the radical sign, we have x is equal to negative 6 plus minus the square root of 372 all over 2, which is also equal to negative 6 plus minus 2 times the square root of 93 all over 2. Notice that we can further simplify the answer by factoring out 2 on the numerator, giving us the possible values of x, which are negative 3 plus minus the square root of 93. The possible values of x are negative 3 plus the square root of 93 and negative 3 minus the square root of 93, which are approximately equal to 6.64 and negative 12.64 respectively. We will be accepting only the value which is positive since x pertains to the length of segment GA. Therefore, the value of x, or the length of segment GA, is negative 3 plus the square root of 93, or 6.64 units. For the third theorem, we have the tangent secant segments power theorem. It states that if a tangent segment and a secant segment are drawn to a circle from an exterior point, then the square of the lengths of the tangent segment is equal to the product of the lengths of the other secant segment and its external secant segment. The figure illustrates a secant segment, segment YO, and a tangent segment, segment CO, drawn to a circle from an exterior point O. By the tangent secant segment power theorem, the square of the lengths of segment CO is equal to the product of the lengths of segment YO and segment NO. In the circle given, segment PQ is a tangent segment while segment PA and segment PM are secant segments intersecting at B and N respectively. First, if PN is equal to 9, PM is equal to 16, find PQ. And if PB is equal to 4 and BA is equal to 12, find PQ. Since the unknown on the problem is the length of the tangent segment PQ, the working equation will be PQ squared is equal to PM times PN. We can directly substitute the values for PM and PN since it is already given on the problem, giving us PQ squared is equal to 16 times 9. Simplifying the right side of the equation and simultaneously subtracting its square root, we will have PQ squared is equal to 144, giving us PQ is equal to 12. Therefore, the length of segment PQ is 12 units. For problem 3b, we will be applying the tangent secant segments power theorem, which will lead us to the working equation PQ squared is equal to PA times PB. Since the length of segment PA is not given on the problem, the working equation will further become PQ squared is equal to the quantity of PB plus BA times PB. That is because segment PA is composed of segment PB and segment BA, which are both given on the problem. Substituting the values given, we have PQ squared is equal to the quantity of 4 plus 12 times 4. Simplifying the right side of the equation and then extracting the root, we will have PQ squared is equal to 16 times 4, which is PQ squared is equal to 64, giving us PQ, which is equal to the value 8. Therefore, the length of segment PQ is 8 units. For the last but definitely not the least, we have the chords power theorem. If two chords of a circle intersect, then the product of the measures of the segment of one chord is equal to the product of the measures of the segments of the other chord. In the figure, segment SN and segment LD are chords. Segment SN is composed of segment SA and segment NA, while segment LD is composed of segment DA and segment LA. Illustrating the chords power theorem, the product of the measures of segment SA and segment NA is equal to the product of the measures of segment DA and segment LA. Applying the chords power theorem, we have this problem. In the circle given, chords AB and MQ intersects at point E. If BE is equal to 5 units, QE is equal to 10 units, and ME is equal to 13 units, find AE. The length of each segment composing the two chords are given. So solving for AE, we will be using the working equation AE times BE is equal to ME times QE. Substituting the given values, we have AE times 5 is equal to 13 times 10. Simplifying the left side of the equation and solving for AE, we will have 5 times AE is equal to 130, giving us AE is equal to 26. Therefore, the length of segment AE is equal to 26 units. So that's all for the theorems regarding the segments formed by tangents and secants. I am hoping that you can now apply the concepts we have discussed in answering the problem and the scenario posted a while ago. See you again in our next lesson, G10. God bless!